Okay, the next example, which is example 2. Let's say the wavelength in vacuum uh, is 633 nanometers. Okay, suppose lambda naught is 633 nanometers. That's the wavelength of this light. In some material, some liquid, some material, lambda is 474 nanometers. Okay, so let's find N, V, and F. What's the index of refraction of this material? What's the speed of light in this material? And what is the frequency? Okay. Any ideas? That's right, yeah. Solution. So you're plugging here. So therefore what? N will be lambda naught over lambda, right? So I have 633 over 474. Everything is nanometers, so they cancel, so I don't need to change. And yeah, again, you should calculate it so you don't, so you're actively doing something. How much? 1.33 set?
1.34.
1.34 approximately? Okay, 1.34. Yeah, so that is the correct answer. Next thing is the speed of light in this medium will just be c over n, right? C is 3 times 10 to the 8 over 1.34, so it'll be a little bit slower. And that speed is approximately 2.25 times 10 to the 8 meters per second. Okay. Now the frequency, we can do two different ways. We know that V is equal to lambda times F, and so F is equal to V over lambda, and V is 2.25 times 10 to the 8th over lambda, which is 474. But that's 474 times 10 to the minus 9, because it's nanometer. Now we have to change, right? Because the speed of light is in meters per second, or the speed is in meters per second, and this one needs to be changed from nanometers to meters. That turns out to be this 4.74 times 10 to the 14 hertz. Okay. And it shouldn't be surprising that you will get the same thing if you do C is lambda naught times F, and F is also C over lambda naught. And you will get exactly the same. Can I erase the left board here? Because I want to do one more, well, a couple more problems. Said I could, right?
Go ahead.
Yeah. Okay. So the third example is two mirrors that are perpendicular to each other. So this is the third example. So example 3. So let's say I have a mirror here and another mirror here, and they're at 90 degrees with each other. This is a mirror, and this one is also a mirror. So light comes in like so. Let's say it comes in at this angle. What happens to it when it hits the mirror? Reflects, okay? Reflects at the same angle or different angle? Same angle. Good. Okay, that's the angle. So let's say this is theta 1. Then this also is theta 1, right? Yeah. Okay. We always measure from the perpendicular. So here's the perpendicular. So if this is theta 1, what is this angle? That should be theta 1, right? They're parallel lines, so theta 1. What would this angle be? 90 minus theta 1. And then it will reflect this way, right? And what would this angle be? This one?
90 minus 7.
Yeah, this should be equal, right? Reflection, 90 minus theta 1. And what is this angle? Theta 1, yeah. So what do you conclude about the two rays? The direction of the incident ray, and then the one that is reflected at the end, the outgoing. This is the incoming, this is the outgoing. Are they, what do you call them? Parallel, perpendicular, kind of skew lines?
Parallel.
Yeah, they're parallel. Yeah. Look at this one. What angle does this, let's say this one makes, let's say 30 degrees, just for the sake of argument. Makes 30 degrees with the perpendicular, right? This one makes 30 degrees with the perpendicular. And this one will also make 30 degrees with the perpendicular. They're anti-parallel, right? This one is coming, this one's not coming. So they're anti-parallel to each other. Okay. And you can see, right, if you make this angle here, instead of 90 to be something else, then the geometry would be a little trickier. So but you have to keep track of all the angles, okay? And okay. All right. Let's see. I have one more question. This one is a conceptual question. It's a conceptual question. And for refraction, I always, I'm just trying to find the picture here. I always fail to draw it nicely. Have you seen, like, when you stick like a pencil inside a cup of water? How does it appear? Bent, broken, right? Yeah. So I'm going to just try to draw how it looks like. How does it look like? So let's say this is some water here. And let's say our pencil looks like this, right? Okay. Now, how do we see things? Does light come from our eyes to the thing, or from the thing to our eyes? From the thing to our eyes. So let's say I'm here. I'm looking at it. This is my eye. So let's look at this one. Just take one point. This point will be given light in every direction. Some of it will reach our eyes. So how do I? Let's say, again, I apologize if I misdraw this. Okay, I'm not the best. So this ray here, in what direction will it go? Will it bend toward the normal or away?
Away.
Away, because higher index to lower, right? This is water, this is air. So it will bend away, and it will miss my eye, so let me readjust, okay? And then let me draw another one, maybe just another ray. So every point can send many rays of light. So let me draw another one. Let's say this one is right next to it. And it will also bend, but it will bend a little bit more, right? Because the angle is more. To our eye, these two rays, they're coming from here. Somewhere in the back. So it seems like the bottom of the ruler, instead of being here, it's actually higher. There is a better picture in the book, so look at it. This is not the best one. Sorry. Okay. So the pencil, if you trace this with every other point will look higher, but then this one will be normal to us because it's in air. So the pencil will look broken. So with that same thing, let's say we have, you're trying to fish and in a pond, and let me make sure I draw it correctly. So this example here is a pond, and here's the water. Here's the fish. Let's make the fish a little bit more down. Some space. Let's say light comes this way, and then it comes to you, right? You're standing somewhere here, let's say. You're standing here trying to catch the fish. So to you, so this is the ray comes from the fish, and then it seems like the ray is coming from a little bit above. So it seems like the fish is a little bit above. Is that clear what I'm trying to draw? This is probably the time where PowerPoint would be nicer to use. But it seems like the fish is actually higher. Okay. For similar reason to this. And you're trying to get the fish. So in the book here it says you're trying to spear the fish. Should you aim your spear at the apparent? This is the actual fish, right? This is real. This is real. This is the real thing. And this one is the apparent. Should you aim your spear at the apparent one, or above it, or below it? Yeah, because the actual fish is here. You want the spear to hit the actual fish. Okay. That's not it. I mean, we're not done yet. So you aim your spear a little bit below, right? How much below? I don't know. You have to do it from experience. But it's below. Now, let's say you have a laser pointer, right? You have a laser pointer now, not a spear, a laser pointer. And you want your laser pointer to land the dot, to hit the fish, to land on the fish. Should you aim at the apparent picture of at the apparent position of the fish, below it, above it? Where should you aim? Yeah, you will aim at the apparent. Because if you aim at the apparent, so now if you send light, instead of light coming from the fish to you, if light goes from you to the fish, it will bend. And this is the path it will take. The path is reversible. If it goes this way, when it starts here, it goes that way. Now if you reverse it, it will go that way. Yeah. Because if this is the path of least time, well, then this has to be the path of least time. Okay? Yeah.
So if you had some sort of like fishing ray gun, you would aim it at the apparent fish and you'd like die?
Ray gun sends light, then yeah.
It says here, it's a funny one, I guess. It says, if instead you use a high power laser to simultaneously kill and cook the fish, both. You want to cook the fish inside the, anyways, it's, anyways, we're about the physics, not the hunting. Alright, so we're going to go on. The next one is about total internal reflection. Total internal reflection, alright? So what does that mean? So let's say, in fact, let me make some use of this board instead. I'm going to let you experience this on your own. Let's say here is medium 1, and 2, and 1 now is water, and 1 is 1.33, and then N2 is 1, okay? N2 is 1. And you're going to aim your below the swimming pool, and you're going to aim your laser pointer in this direction. Let's say you aim at 40 degrees. Okay, that's theta 1. Would theta 2 be bigger or smaller than 40? When it comes out, will it come like this or that way?
Away from, towards the normal.
Towards the normal, it's going to be
Which is,
towards the normal, it's going to be smaller? Okay, well, I'll let you discover that. Why don't you calculate it? Find theta 2.
no, it's gonna be away.
It's going to be away? Yeah, it is going to be away. Yeah, so why don't you calculate that? Why don't you calculate theta 2? I'll let you calculate theta 2. Give you a moment. Use your calculator. Should be more than 40. So if theta 1 is equal to 40 degrees, then theta 2, you will use Snell's law, right? N1 sine theta 1 equals to N2 sine theta 2. N1 is 1.33, N2 is 1. So you have theta 2 will be the sine inverse of 1.33 over 1 times the sine of 40 degrees. You said 50?
59.
59 degrees approximately. Okay. So let me just make it 59. And you can see this angle is 59. Let me have you do one more quickly. What if theta 1 is 45 degrees? If theta 1
Would be 70.
would be 70?
Yep.
Okay. So you can see, is there a problem with this? Can theta 1 keep growing? Now, what's the maximum theta 2 can be?
90.
90. Yeah, I mean, 90. And that's it. Beyond that is what happens. So the angle at which you get 90 is called the critical angle. Okay? Is the critical angle. So the angle at which, if theta 1 is large enough that theta 2 is 90 degrees, that's called the critical angle. At that critical angle, what happens is none of the light is refracted. Nothing comes out. What you will have, all of it will be just reflected. It will just reflect down, and it's called total internal reflection. Okay? So at what angle, so what is the critical angle? So let me write it here. State the problem. What should theta 1 be so that what? Theta 2 equals to what? What do I want theta 2 to be? 90 degrees. Okay. All right. So what should theta 1 be? Well, you got N1 sine theta 1 is equal to N2. What's the sine of 90?
1. So that's it, it's just equal to N2. So we get theta 1 will equal to sine inverse of N1, no, the sine inverse of N2 over N1, right? Sine inverse of N2 over N1. And what is sine inverse of 1.33, no, 1 over 1.33?
48.7.
Huh?
48.7.
48.7, thank you. So that's the critical angle. Okay. Beyond this, none of the light will reflect. So if I have, let's say 48.7, let's say 49. If I have a 49 degree angle, let's say this is 49. What happens? All the light gets reflected. None of it goes out. That's called total internal reflection. Total internal reflection. Now, total internal reflection only happens if N1 is larger than N2. It only happens if N1 is larger than N2. It can't happen if N2 is larger than N1. Because think about it. If N2 is larger than N1, what would you get? Let's reverse that. If you have 1.33 over 1, that's 1.33. What's sine inverse of 1.33? Does not exist. Sine cannot exceed 1. Okay? The sine cannot exceed 1. Which makes sense, because if you start here, the light always bends toward the normal. So what happens is, if you start here, you will reach 90 degrees here before this one reaches 90 degrees. So it's not possible to have total internal reflection in that case. But if N1 is larger than N2, then it is possible to get total internal reflection. Okay? Let's do the following. I'm going to ask you the following question. Suppose I have glass, 1.52. So here is glass, this example. We'll do 2 more and that's it. Example.
Professor?
Yes.
So there will be a ray that will be at the surface, right?
What do you mean?
Because you say theta is 90.
And here I'm exceeding it.
No. Is there any way that is like at the surface, because you say theta 2 is 90 like that?
Like this?
Yeah.
No. You will get the barely touching if you're at this angle.
Okay.
That would be 90, right? That's
Okay.
90. But here I'm exceeding it. As soon as I exceed that, there is nothing here.
Okay.
All of it will just vanish.
Okay.
Yeah. And there is a formula or an equation for calculating the intensities. As the angle grows, that intensity will just go to 0.
That was going to be my question about the intensities.
Yeah, it depends on the angle, and at the critical, it's gonna just go to 0. Yeah.
Never mind.
Oh, okay. You answered your question?
Yeah.
Okay. So let's say N1 is glass, is 1.52, okay? And N2 is air, and that's just 1, right? Approximately 1. And let's say I have light, starts here. 1, and then theta 2. What is the critical angle? Theta C. Can you guys find the critical angle? Very similar to what we did. Let's find the critical angle for this glass. You will have sine inverse of something, right? Sine inverse of 1 over 1.52. Yeah, what would it be in degrees? Thank you. 41.1 degrees. Yeah. So if you exceed this angle, what happens? Any light escapes? No, you will have total internal reflection. Okay? Total internal reflection. And I'm going to give you an example and then an application of this total internal reflection. So here is the example. Consider a prism that's a glass prism, made of, it's 90 degrees. It's like 90 and then 45, 45. So let's, I'm going to orient it this way so that, does this look like 90? Yeah, this is 90, okay? So if this is 90 and it's equilateral, so what would this angle be? 45, right? This is 45, not equilateral, isosceles, sorry. Just the two sides are equal. 45 degrees. Okay. So, yes? Does that make sense? 45 plus 45 plus 90. Okay, good. All right, so first question. Let's say I have light. Okay, light that's incident straight. That's horizontal. All right, so please pay attention with me. Let's use blue. Okay. Question 1, right? What's the angle of incidence here? Yeah. Huh? 90? It makes 90 degrees. Remember, we measure it from the perpendicular though.
0.
0. Yeah, the angle it makes with the perpendicular is 0. So the angle of incidence is 0. So my question to you, then, this ray, because it's here, is it going to bend this way, upward, or maybe pass straight? What do you think?
Passes straight.
Passes straight because n1 sine theta 1 equals to n2 sine theta 2, right? Theta 1 is how many degrees we said? 0. So n1 sine 0 is 0. Left side is 0. Right side, you have n2, that's something, you can't do much about it. Sine theta 2. So I need sine theta 2 to be 0. So theta 2 must be 0. So it cannot bend. It just has to go straight. Okay. So if the light is incident normal to the surface, it will just pass through. So it goes this way. All right. Clear? Next. Now, I'm going to draw perpendicular so we're clear. So here is a perpendicular to this surface. What angle does this incident ray make with this perpendicular?
45.
That's 45, right? Because it's 45, 90. Yeah. So if this is 90, yeah, this is 45 and 45, right? So this has to be 45. Okay. Let me draw. That's 45. How much light comes out? Or what? Will any light come out and refract? Remember, this is glass. It's the same. This is glass. Yeah, maybe I should have written. This is glass. Will any light come out?
Yes.
How much or why?
How much?
Yeah.
It would, because it's glass. I mean, it wouldn't get reflected unless it's the angle.
Critical angle?
The critical angle.
What's the critical angle? 41.1, right?
Yeah.
Does this exceed?
Mhm.
Yeah, it's 45. So no light comes out, it all reflects. Total internal reflection. Okay? Because this, we said 41. So this one already exceeds that. So all of it will reflect. Now, angle of incidence equals to the angle of reflection. This is the angle of incidence, it's 45. So the one reflected has to make 45, right? How does it look like if it's 45? 45 plus an additional 45 would be here, right? So it would come straight down. It'd be coming this way. Because this is 45, right? Of 45. Right? Okay, you tell me now. This is how much light comes out here?
No.
Nothing. Yeah. Why? Because what's the angle of incidence on this surface now? let's use red maybe here. So here is the perpendicular. This angle is, that's 45. So that exceeds the angle of the critical angle. Therefore, it will reflect, and it goes this way. So, but this angle here is 45, right? Because angle of incidence equals angle of reflection. And now when it comes out, does it go straight or bend either way, up, down?
Straight.
Straight, because it's the angle of incidence here is 0. That's the way it comes out like that. Okay. Make sense? So there are many applications of this. One of them is for fiber optics. Have you seen those? Many, like a bundle of fibers, and then you put it on a sheet of paper, and then you would be here. You're not looking straight at the paper, but then you can see the letters. You can read them fine. How does it work? It works this way. So let's say it's circular, like this, or cylindrical, I should say. Let's say you're here. Right? This is the page you're reading, and your eyes are here. So whatever light comes out from here will be from here. So let's see why that is. So let's say I have some letters I'm reading. So how do we see? Light, right? Light from there. So let's say I have light that goes in this way. And the fiber optic will have an index of refraction that's high, such as maybe 1.52, maybe 2. I think some of them are like 2.5 or something, some large number. Okay. So if it's 2 something, you can do the critical angle. If it, right, think about it. Let's say the index of refraction is 2 or 2.5. What would the critical angle be? So let me write it here. So let's say if N1 is at 2.5 and N2 is 1. What's the critical angle? Can someone do the calculation?
23.6.
23.6. A small angle, right? 23.6. So as soon as, if you exceed this angle, what happens? Total internal reflection. So here's an incident ray. Here's the perpendicular. Right? We have to draw a tangent and then a perpendicular to it. So the perpendicular looks like this. So let's say the angle of incidence here looks close to what, 30 or 45 or something like that. So how much will get out? Nothing will leak. So all of it will be internal reflection. So like something like that. And now you look here. There's that. So the perpendicular is here. So it will again, angle of incidence equals angle of reflection. None of it comes out. So maybe here, sorry, it wasn't so straight, but you get the idea. So the other one here, it will reflect until it comes out. So basically the light keeps reflecting until it comes out from there, and the intensity will be pretty much the same as here, so you can see fine. Provided that you don't make too sharp of angles. Don't make too sharp of angles. And those bundles don't allow you to bend them too much anyways, otherwise you break it. Okay. The next, the book has some discussions on the many applications. The next topic is dispersion. Let me pause this for a second. So, one more topic, 2 more topics, as I mentioned. Dispersion and polarization. So dispersion is the dependence of the wave or the index of refraction on the wavelength. Okay. So different wavelengths, they experience different index of refraction. Okay. Different wavelengths, they experience a different index of refraction. So for example, let's say I send light through a prism
it should be like a, let's say, a prism that looks like, yeah, maybe that looks something like this, where the angles are not necessarily 45, they're smaller. So if light comes in, maybe like this, light comes in like this, here it doesn't bend, right? Because it's 0 degrees. But then here, in here, as it exits, will it bend toward the normal or away from the normal? This is probably not the best example. I should have chosen this side of the prism. But let's say it will bend away from the normal, like so, right? Different wavelengths, they experience different index of refraction. So let's say, starting from the longest wavelength, which is red, to the shortest wavelength, which is violet or blue, they experience slightly different index of refraction. So they bend slightly more. If it's a blue light, it will bend a little bit more than red light. Yeah.
So then do they have like a constant for each?
Yes. Yeah. So let's say glass, you get 1.52, right? Maybe. I mean, there are the numbers here. Let's say, I'm just making up the numbers. For glass, let's say for red, it's 1.52. For blue, it might be 1.521 or 5. And then maybe for orange, it's somewhere in between. So they all bend differently. So what happens if you send white light, which is a combination of all the wavelengths, right? Of all the wavelengths. So what happens to all these wavelengths? Yeah, they separate because they bend differently. So the blue will bend the most, and then green, yellow, and orange, and all the lights, they will bend different, and it will separate, and you will get like the rainbow color. It will separate. That's called dispersion. Yeah.
Does it have anything to do with the energy? Because the blue light has more energy.
Yeah, it does have more energy. Yeah. I don't think we mentioned those yet.
Okay.
Yeah. Yeah. So let me see here. So that is really that is dispersion, and it's just an application. It says how the rainbow forms from the droplets of water. You have sunlight going through the droplets of water in the atmosphere, and it bends differently for different wavelengths, and so it separates, and you get the rainbow. So that's that section. There is nothing in it. Then comes the topic of polarization. Okay, of polarization. So imagine I am walking with I have a meter stick here. I wish I had a 2-meter stick. And if I'm walking through the door, and my meter, I will make it through the meter stick, right? But if I walk through the door this way, I can't make it through the meter stick, or the meter stick cannot make it through it. So what a polarizer does, if you have an electric field, let's say up and down, it's going like this, and your polarizer only allows that, any electric field that's going horizontal like this, it will not be allowed through. It will not pass through.